Have you ever wondered why some electronic devices respond instantly while others seem to lag, especially when dealing with rapidly changing signals? Or perhaps you have considered what truly limits a transistor's ability to switch on and off at incredible speeds, defining the very performance of modern digital circuits. The cutoff frequency is critically important for transistor switches because it defines the maximum frequency at which a transistor can effectively amplify a signal, or in switching applications, how quickly it can transition between its on and off states. It essentially sets the upper limit for the speed and responsiveness of your circuit. This limit arises primarily due to the internal parasitic capacitances within the transistor, specifically the junction capacitances between the base, collector, and emitter regions. When a transistor tries to switch, these capacitances must charge and discharge. The higher the frequency of the input signal, the less time there is for these capacitances to fully charge or discharge, which delays the response and causes the transistor's gain to drop. Imagine trying to fill and empty a bucket very quickly. At some point, you just cannot keep up. The cutoff frequency is the point where the common emitter current gain, or beta, falls to 1, meaning the transistor can no longer amplify. For switching, this means the turn-on and turn-off times become too long to respond to the input changes, leading to signal distortion or complete failure to switch. Understanding the cutoff frequency allows engineers to select the appropriate transistor for a given application. If you need a switch that operates at megahertz or gigahertz speeds, you must choose a transistor with a cutoff frequency significantly higher than your operating frequency. This knowledge directly impacts circuit design, preventing issues like slow switching speeds, increased power dissipation during transitions, and overall system instability. For instance, in an oscillator circuit, selecting a transistor with insufficient cutoff frequency would simply prevent it from oscillating at the desired rate. Engineers often use the term transition frequency, or FT, to characterize a transistor's high-frequency performance. It is a key parameter found in a transistor's datasheet, indicating its potential speed. Knowing this value allows for optimizing layouts to minimize stray capacitance and inductance, further pushing the limits of switching speed. For digital systems, exceeding the FT rating of a transistor means losing data integrity, because the on and off states cannot be reliably achieved within the given clock cycle. Ultimately, a solid grasp of cutoff frequency ensures that your transistor switches can keep up with the demands of modern electronics. It is not just a theoretical number. It is a practical guide for designing high-performance, reliable circuits that function exactly as intended, underpinning everything from microprocessors to high-speed data communications.